Okay, welcome everybody and welcome to today's show. Today we are gonna check under the hood how this command works, or this code rather. If you have been following my C series, this should not really be news to you, what this command does. So, PRINTF hello world. What happens in the operating system, in the CPU, when we issue this command? PRINTF is a library call. So the C implementation consists of, on the one hand, all the additional packages that you can install and header files and so on. But in its base, there is a standard C library. It's called libc or glibc, which contains all these functions. And when you look into the man pages, for example, that's when you do man 3 and then a command, then you look at the library functions. So, for example, this is the printf man page. But there is one additional level, and that is system calls, or syscalls. And that is basically what we tell the operating system. So printf and other library calls, that is communication between the programmer and the userland software. But then the actual software needs to communicate with the operating system, and that's done via these system calls. So printf, for example, turns into a system call called write, which is used for writing to files, but also for writing to special devices like the standard input and output, like the screen and the keyboard. And then in the next level, the operating system communicates with the CPU, the central processing unit in your computer's hardware. And we're going to take a look at that as well. But let's start with the first level. So we'll create a very simple C program, probably the first one you ever did, a hello world program. And I'm currently using Nano for this. I will probably be using VI when I do the more advanced stuff. But you can use Nano all the way if you don't know VI. Okay, printf, and I usually put in this return 0 line as well. I like structure. Okay, so let's save this one, a.c, and we do gcc, and as expected, it prints hello world to the screen. Okay, no surprises there, but if we don't want to use library calls, perhaps we do this in an educational fashion to learn, or we want to improve the performance of our program. Then we can use the write system call directly. And if we go to the man page, and to access the man page of a system call, you do man2 instead of 3, and then the name of the system call, like right. As we can see, it requires one header file, unistd.h, and it takes 3 arguments, one file descriptor. That is, when you open a file, you get back a special value which is used to link that file to your other commands. So like you get one of these FDs when you open the file, and then when you write or read to the file, you supply this FD so it knows what files to open or write and read. And then we have a buffer. So that's basically, well, the variable where you want to where the text is located that you want to print in this example. And then a count. How many characters do you want to print to the screen in this case? And then it returns this is an integer value, how many bytes were written to the file descriptor. So not too complicated. And let's create a what should we call it? B.C. That'll be good. And we need the standard input output library, and also this unistd one, like this. And then we do write. And what file descriptor should we use? If we open a file and we want to write to a file, we get that returned to us. But we are not opening a file now, we are writing to the screen. So there are 3 special file descriptors which are always open. And that is 0, which is standard input. That is the keyboard, usually. And then we have standard output, the screen. And then we have one additional one, which is called standard error. And that is usually also the screen, but in a little different fashion, so you will be able to differentiate between these two. But don't worry too much about that. We want to use this second one with the number 1. So we are writing to the screen. So we put a 1 right here. The second argument is a buffer. So here we put the variable or the text string we want to print. Hello world, new line. And then we need the size of this. So either we count it manually, or we can do something like string length of hello world. But I think I will just put in 5, 10, 11, 12. At least if I spell this correctly. And that's it. So let's return 0. And we compile b.c to b2. And we get hello world. There is a good Linux command that you can use to debug when you're using syscalls. and even when you're not, because there's always a syscall in the background somewhere, you can use strace. So you do strace.f, dash f, I mean, and then you type in the name of your binary, and then you get a lot of information. But the interesting thing is this right here. So we see that we sent a write request to file descriptor 1, hello world, and size 12. And then we see the result directly after. So this is a really good way to test your and debug your code. And I just noticed that I started up the wrong binary before. This is the right one. Okay, so now we know what happens at the library level and what happens at the syscall level, the operating system level. What about the CPU? What happens in machine code, so to say? To demonstrate that, it's easiest to do a little assembler, because assembly language is basically machine code. So you send commands directly to the CPU. So let's start a file that we will call abc.asm, and I want to code 32 bits assembly, and we will create a section for data. That's where we store our variables or the data. And then we have a section called text. And here is all the instructions for the CPU. And we start every bit of code with defining the start point, the entry point of the program. And then we put the label right here. Okay, so we're going to start with a real simple code. We're going to do exit 0 in C in assembly. So we're just going to exit our program to begin with. And you do it like this. In the AX register, that is, the registers are like variable space, but in hardware. So you can put one number in each register. And it's a very fast kind of memory. So in the first register, it's called EX. There we decide what system call to use. And I will put a 1 here, which will correspond to the exit system call. In the second, called EBX, we put the first argument to the system call. And as you might remember, let's put a comment here with our write command. So first we have the FD, then we have the buffer, and then we have the size. So into EBX we'll put the 1 for the file descriptor 1. Then in the third register, ECX, we put the buffer. So what do we put here? Well, first we need to create the text string in the data part, and we give it a label. So let's call this string, and we use the db command to put specified bytes directly into the memory. And we'll put hello world, and we can't do the \n in new line because the CPU and the operating system will not evaluate that. However, we can put the hex code for it, and the hex code is A. Oh, sorry. A. And then I'll put 0 at the end to end the string. But I'm getting a little bit ahead of myself. Let's remove a little bit of this. First, I said we're going to do the exit first. So let's begin there. So I'll create a label called exit, and the first system call is exit, as I said. So we put it into EX, and in the first and only argument in the EBX, we put the return code. So every time it's like the return 0 in C, that it closes down the program with a 0 as the return code. And we can specify what we want to have here. So let's put a 5 in there just to notice it. And then we do an interrupt with the hex value 80. That basically says now the operating system should take over and print this to the screen with the help of the central processing unit. So you always fill in these registers and then you end by int 0x80. Okay, so let's save this, and then I will use NASM to compile this or to assemble this. And I'm using a 64-bit CPU, so I need to convert it to ELF64. And the name of the file is abc.asm. And now we created an object file, abc.o, which we will just link in to a binary. So ld_abc.o, and as output we name it abc. And then we run it, and we don't see anything. But if we add a ampersand at the end and press enter a couple of times, we see the exit code right here. So it works this far. Let's go back into the code and do the write function as well. And the syscall number for write is 4, so we put it right there. And into EBX we put the 1 for the file descriptor. Like this. And into ECX, that is the buffer. And we named our buffer str. So we just put str right here. And then the assembly program will replace the string str with the address to the actual hello world string. And EDX should contain the size to write to the screen. And hello is 5, world is 5, there's a space, that's 11 total, and then the new line as well, so 12. And finally we do the interrupt as well. And if we were to have just this, then it would print and then crash. because we always need to exit the program cleanly. So I will keep the exit right here. I will just change the exit code so we see that we can change it as well. And then we save, and we run NASM, we run LD, and we start ABC. Hello world. And if we add the ampersand, we see that it's let's do like this instead. Strace. There we go. Exit 0. And here is our write command as well. So this is what happens on the 3 levels. If you like this video and you want me to do more videos like this, hit the like and subscribe button and tell me in the comments. And thanks for watching, and thanks for today.